Again, our new technique here was if you have the same base on each side and then an exponent and nothing else, it's got to be base raised to exponent equals base raised to exponent, nothing else, then you can set the exponents equal. Now the technique does not apply directly to 6 to the x power equals 36 to the 3x plus 7 power. Right? Now, even though both sides are the form base to an exponent, base to an exponent, it doesn't apply because we need the bases to match. But we don't have matching bases. We have a base of 6, and the other base is 36. So we're going to have to do something first. To solve the equation 6 to the x equals 36 to the power 3x plus 7, we should try to get the bases to match, but we can't just change this 6 on the left into a 36. We can't just change the 36 on the right into a 6 because 6 and 36 are not the same number. However, we can, in trying to get the bases to match, a way to write 36 is we can write 6 to the second. So 6 to the second is a legal, it's a valid way to replace 36. So 36 gets replaced with 6 to the second. There's still this exponent of 3x plus 7 there. Then we apply one of our rules for exponents, which is when you have exponent raised to an exponent, you get to multiply the exponents together. So the right side, just to take it one step at a time, is rewritten as 6 to the power exponent times exponent. So 2 times quantity 3x plus 7. That's due to this very old exponent law that says a to the m quantity to the nth is equal to a to the mn. So m here is 2 and n is 3x plus 7. Now take a look at the equation. We've got base to an exponent equals base to an exponent. And now the bases match. Both bases are 6, so we can set the exponents equal. We have x as one exponent over here equals, and then the other exponent is 2 times quantity 3x plus 7. So now we can distribute 2 on the right side, so 6x plus 14. Let's subtract 14 on each side, subtract x on each side, so negative 14 equals 5x. Divide both sides by 5, and negative 14 fifths is equal to x. Now, you'll notice that what we did was we turned 36 into 6 squared because, well, 36 is 6 squared, right? Sometimes people make errors in this process and they just try to make up anything. So just be careful. Don't turn 6 into 36 squared because, well, 6 is not equal to 36 squared. Again, comment here, 36 turns into 6 squared because 36 is actually equal to 6 squared. But don't turn 6 into 36 squared because, well, 6 is not equal to 36 squared. Don't turn 36 into 6 because 36 isn't equal to 6. Don't turn 6 into 36 because, well, 6 isn't equal to 36. You can turn 36 into 6 squared, which is what we did here. This 36 that's right here became 6 squared. Okay, well, this new technique doesn't apply to the equation 9 to the x squared equals 3 to the 3x plus 2 because the bases don't match. We have a base of 9, we have a base of 3. So what we can do is we can change that 9 into a 3 squared. So the 9 that's here turned into a 3 squared. And then we have that exponent formula from way back when in the second week of the semester, and we can multiply the exponents together. So this is 3 to the power, now 2 times x squared is 2x squared, equals, and then the right side has just remained the same the whole time, 3 to the power 3x plus 2. Now we can apply the new technique because both sides are base to an exponent only and the bases match. Since the bases are both 3's, don't put slashes through the 3's, just set the exponents equal. We have 2x squared is equal to 3x plus 2. This is a quadratic equation. Let's get all terms on one side. So subtract 3x on both sides, subtract 2 on both sides, and you end up with 2x squared minus 3x minus 2 equals 0. The left side, I know it's a little extra work due to the coefficient not being a 1 in front of the x squared, but this does factor. You just gotta, check a couple scenarios. Good thing 2 is prime, so 2 is either 1 times 2 or 2 times 1. Same deal with negative 2. Okay, so this will factor as 2x plus 1 times x minus 2 equals 0. We can apply the zero product property and end up with x equals negative a half or x equals 2. Again, some comments are in order. First of all, an alternate way to do this is if you want, instead of changing the 9 into a 3 to the second power, you can keep the left side being 9 to the power x squared, and you can change the right side, This is probably not the way that people will do it, but I just am arguing a point that you can do it this way. You can change the 3, so keep the 3x plus 2 power, but the 3 that's the base could be changed to a 9 to the 1 half power, because 9 to the 1 half means that, well, another way to say saying 9 to the 1 half power is a root 9, which is a 3. So 3 can get replaced with root 9, and another way to say root 9 is 9 to the 1 half power. And then if you do this, you can, just talk about saying, okay, that 1 half exponent times the 3x plus 2, so you have 1 half times 3x plus 2 as the exponent now. And then now that you have both base 9s, you can set the exponents equal, have x squared is equal to 1 half times quantity 3x plus 2, and the work will then look very similar to what we had before. Okay, let's solve 27 to the x minus 1 power equals 9 to the power 10x minus 3. Now here's the thing, 27 isn't easily written as 9 to a power. 9 isn't easily written as 27 to a power. That's in the previous equations that we solved, we either modified the base on the left or the base on the right. Here for this problem, it will be probably most convenient to modify the base on each side. So change the 27 into 3 to the third, because, well, 27 equals 3 to the third. Change the 9 into 3 to the second, because, well, 9 is equal to 3 to the second. And then apply the law of exponents that allows you to multiply those exponents together. So the left side becomes 3 to the power 3 times quantity x minus 1, whereas the right side is 3 to the power 2 times quantity 10x minus 3. Okay, we haven't applied the new technique yet. We've just kept rewriting the left side and kept rewriting the right side. But now the new technique applies because we have the matching base. So we set the exponents equal. We have 3 times quantity x minus 1 equals 2 times quantity 10x minus 3. This, as we look ahead, is not even going to be a quadratic. It's going to be a linear equation. We can distribute on each side. So 3x minus 3 equals 20x minus 6. Let's subtract 3x on both sides, add 6 to both sides. You'll have 3 is equal to 17x. Then divide both sides by 17. So 3 over 17 is equal to x. Okay, let's try another one. 1 half to the 6 minus x is equal to 2. It'd be nice if both bases were 2, and 1 half can be replaced with, well, 2 to the negative 1. So this requires some real practicing of things like negative exponents and so on. So remember that 2 to the negative 1 is 1 over 2 to the positive 1. So this 1 half, another way to write it is 2 to the negative 1. All we're doing is work that's in anticipation of using the new technique. Trying to make this kind of fit the framework of what we've seen in some of the previous questions. So before applying the new technique, we can't have base to an exponent. Let's apply a law of exponents that lets us multiply these exponents together. So we'll have the left side is rewritten as 2 to the power negative 1 times quantity 6 minus x equals, and then the right side that just used to say 2 is now 2 to the 1. Now that we have base to an exponent equals base to an exponent, and the bases match, they're both 2's, we can set the exponents equal. So we have negative 1 times quantity 6 minus x is equal to, well, 1 is the exponent on the other side. But we just applied the new technique. Now we can distribute negative 1, have negative 6 plus x is equal to 1, and just add 6 to both sides, and you have x is equal to 7.